No, that's a woman default. We go to tears, they go to swearing. Did you drop an F-bomb? We women, that's our default. We want to cry. It's just the way we're wired. So just a reminder of definition of a polynomial. Reminder of the leading coefficient definition. That's back from last unit. We talked about that. And in case you didn't know, graphs of polynomials are smooth and continuous with hills and valleys. They're not straight lines, they're bumpy.
The exception to that being
Linear, which is the first one we're going to talk about. So the very, very first polynomial you met had a degree of 1. We called it linear. Which, as you know, is y equals mx plus b. And it had that other form that we called standard form that went ax plus by plus c equals 0. Remember that? Yes and no, I heard at the same time.
so x plus by plus c equals 0.
Kinda. And so there's two different cases you can have with the line, and we haven't talked about this vocabulary before, but you can have a leading coefficient that's positive, or you can have a leading coefficient of negative. What that means in terms of this line is the slope is either positive or the slope is negative. So this would be m is positive, m is negative, because the leading coefficient is the coefficient of the x to the 1 in this case. And you know that when the leading coefficient is positive, it's a line that increases from left to right. And when the slope is negative, what does the line do? Decreases. So this is nothing new. This is just taking stuff you learned in grade 10. You probably hated that unit. Everybody does.
But now it's easy compared to some of the stuff we're doing in like guess and check too.
Everything's easy when you look back. And so we let lines simmer in grade 10, and then when you came to grade 11, you were ready for the second degree polynomials, and what did we call them? Parabolas. And then we had another name that we often called them. Quadratics. And that's y equals ax minus h squared plus k. Or we had the other form when it's not in completed the square form that said it's ax squared plus bx plus c equals 0. And you probably never put these two together, but if you look at the two standard forms for them, they're very similar. So this has an a, a b, a c, this has an a, a b, and c, this has an x, this has an x squared, and an x. Positive leading coefficient, what it meant in this case is that the x squared was positive, and then the x squared was negative. Ooh, x squared, negative. And so what does a parabola look like when that first term is positive? Goes up. And then when we stick the negative in front, you now know from transformations that's a vertical reflection, and what happens when we vertical reflect it. And then we let those simmer all through grade 11, and we came back to them a bunch of times. And then in transformations, we're like, you're ready to meet x cubed. What did we call x cubed graphs?
Third degree graph.
Cubics. Cubics. And they only have, well, they've got two forms, but you'll never meet the other form. So their general form is ax cubed plus bx squared plus cx plus d equals 0. Yeah, well, it's got a factored form, but we don't really use it. So if we start to look at these standard forms, one next to each other, you notice we're just increasing the degree each time. So this has an x to the 1, this has an x to the 2, this has an x to the 3. And we kind of started to look at this in transformations, but the cubic generally starts at the bottom, has a max and a min, and goes up. So it's our snake graph. We only looked at the base graph, so it wasn't quite as snaky as this one will be. But the difference from the quadratic is the quadratic had a max or a min. The cubic has a max and a min. This had a max or a min. This has a min and a max. This had nothing because it was just a line. Okay, well, what do you think it's going to look like if the first term is negative? So instead of starting from the bottom, it's going to start right at the top because it's just a reverse or a vertical reflection. It's still got a min and a max, and it goes down. And the height of these bumps will just be determined by the values of A, B, C, and D. So as we change the values, they'll get bumpier. We call these hills and valleys, okay, for obvious reasons, because we're not creative people. Well, now it's time to meet x to the fourth. He's called a quartic. And his form is ax to the fourth plus, let's see how much we can figure out the pattern here, bx cubed plus cx squared plus e, because we're not creative, we're just using the alphabet in order. You don't flip, you just keep your page, I'm going to flip. Linear had no max or mins. Quadratic had one max or min. Cubic had two max or mins. What do you think is going to happen here? 3, it starts from the top, gives a min, gives a max, gives a min. Hello, letter W. So we've seen the V, we've seen the U, now we've seen the W. That's what a quartic looks like. And again, the height of the bump just depends on the numbers that are in the equation. That's if the first term is positive. What do you think happens if the first term is negative? So it comes from the bottom, gives a max, gives a min, and back down. X to the 5, quintic. Ax to the 5 plus 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 plus, wait for it, that's right, f equals 0. You keep your page, I'm going to flip back. No max or mins. 1 max or min. 2 max or mins. 3 max or mins. 4 starts from the bottom. Max, min, back up towards the top. There is a quintic. So we'll say it has 2 hills and 2 valleys because there's 2 mins and 2 maxes. What does it look like if the first term is negative? Starts from the top, min, max, min, and down. So we want to talk about what's called the end behavior of the graph. And the end behavior means the arrows. We want to know, are they pointing up or pointing down? That's the key here. We're going to group the odd ones together, and then we're going to group the even ones together. Odd degrees mean a degree of 1, 3, and 5. So let's look at the degree of 1. What do you notice when the leading coefficient is positive? Well, the left goes down and the right goes up. Let's check if that happened with our cubic. Left goes down, right goes up. Same thing. Let's look at our quintic. Left goes down, right goes up. So in general, for any odd polynomial graph, if the leading coefficient is positive, the left-hand side goes down, while the right-hand side goes up. That's going to happen with any odd exponent, odd degree. So if we went forward from our quintic and did x to the 7, it would have the same property, x to the 9, x to the 11, x to the 13. If it's negative, the reverse is true. So let's just look at the graph to prove that. If it's negative, the left-hand side goes up, right-hand side goes down. Here what happens? Same thing, up, down. Let's look at our quintic, up, down. With me so far? Let's look at the even degree. So that would be our parabola and our quartic. Let's look at our parabola. When it is a positive leading coefficient, it is up, up. When it is a negative, it is down, down. Let's see if that worked with our quartic. Up, up, down, down. So for the behavior of an even polynomial graph, for a positive leading coefficient, the left-hand side goes up, while the right-hand side goes up. For a negative leading coefficient, the reverse is true, down, down. What about the number of max-mins? So a linear function has 0, quadratic has 1, cubic has 2, quartic 3, and quintic. So if I gave you an n-degree polynomial, n minus 1. That's very right brain because it's with words. I'm going to give you a chart that's left brain. You can use whatever you want to remember. My brain just works in charts, so I like to do charts. What's the matter, Cole? You look like you're holding your eyeball in. Is this causing your brain to leak? There's one here for you, Andrew. This is just going to summarize exactly what was in the notes in words. We need to categorize them into odd and even, and then we just need to categorize with positive leading coefficient, negative leading coefficient. What I do for odd is I think of a line, because you're used to drawing lines. You drew a million of them in grade 10. You know what they look like. What I picture for the even is a parabola, because you drew a bunch of them last year. You know what they look like. So if you have a positive coefficient, that means the slope is positive. What does the left-hand side do? Left-hand side goes down. Right-hand side goes up. That's notation that makes sense in my head. If you need words or you need LHS, RHS, add those in, whatever you need to understand this. Trick is you need to know by the end of today for an odd degree polynomial with a positive leading coefficient, it goes down on the left and up on the right. With a negative leading coefficient, I think of a line that goes down, because again, you've drawn these forever, you know what they look like. And if you picture the line, the left-hand side goes up, and the right-hand side goes down. Again, however you want to code that is totally up to you. For an even, I think of a parabola, because we've drawn a bajillion of them. If you picture it, it's an even degree, and it's positive, meaning it's pointing up. The left goes up, and the right goes up. They both go up. For a negative leading coefficient, I think of a down-facing parabola. Left goes down, right goes down. We'll come back to this bottom box in a second, but just want to make sure you understand this. It doesn't matter if you memorize it with words, if you memorize it in a table, if you memorize it with the picture, it's completely up to you. You need to know for an odd and even degree polynomial, what does it look like if the leading coefficient is positive, and what does it look like if the leading coefficient is negative. Example number 1, we're not even going to get to the graphing yet. For each of the functions below, we want to know what's its degree, what's its name, what's its odd or its end behavior, and what's the number of max-mins. We're just going to do this orally. We're not going to write it down. A, f of x, 1/3 x plus 4. Give me its degree. Well, you look at the variable and you look for the highest exponent degree is. Fine, just steal that from me, 1. Because it's a degree of 1, what's its name? Linear. How, or what's the end behavior? So what you're looking at is the number in front of the x. Is it positive or is it negative? It's positive, so picture a line in your head that's going upwards that has a positive slope. That means the left-hand side goes down, right-hand side goes up. How many max mins? We'll take the degree in minus 1. So it's a degree of 1. It means it has 0. So I'm just going to repeat that. It's a degree of 1. It's a linear graph. Left-hand side goes down. Right-hand side goes up. Number of max mins is 0. Find a friend, do B, C, D, and then we'll discuss in a few minutes. Just talk about it. Yes, sir. You're throwing me off this week. Okay, C is a polynomial. That didn't sound convincing. Is it polynomial? Yes. What's its degree? What's its name? Either one, I'd accept both. Okay, is the leading coefficient positive or negative? So picture a down parabola in your head because it's going to help get the end behavior. Left is down, right is down. So down, down. Number of max mins? How do you know? Awesome. D, is it a polynomial? Degree? Ooh, anyone get tricky on that one? So does the first one have to be this degree? No, so make sure you're looking through all of them. This might also change the end behavior if you didn't catch that negative 3 is the leading coefficient. Okay, so the end behavior has to be up, down, because it's the negative 3 that determines it. And the number of max mins? 4. That's the theory we need to graph. Are you okay with the theory so far? Okay, so let's actually do what this whole unit's about, which is graphing. You're going to need paper, which I assume you probably already figured out, and you already have that ready to go, and except for Sean, because of bad Ben. Very good. Step number 1, 2, and 3 are in your head. So for the first example, I'm going to show some work, but we normally would do the first 3 things in your head. So when you look at a question, the first thing you want to do is name it, figure out the end behavior, and picture what it's going to look like. All of that's going to give you an idea how to draw the graph. When we actually start doing calculations, we're going to find the x and y intercepts. And then number 5, we're going to use a table of values to find the behavior of the graph around the intercepts. I'll explain that when I get there. So again, I don't usually write steps 1 or 2 or 3. I'm just going to do it for the first one to show you what's going on in our thought process. I kind of felt like singing there, but I will not. Step number 1, name the polynomial. Cubic. Step number 2, look at the leading coefficient, decide on the end behavior. It's a cubic, so you're picturing a line because that's an odd polynomial. Picture a negative slope of a line. What does the left-hand side do and what does the right-hand side do? And if you're visual and you want to draw it, then draw it. Left-hand side goes up, right-hand side goes down. Number 3, just picture the graph. So what does it look like, a cubic that has this end behavior? Well, it's got to come from the top, max and min, and then go to the bottom. Again, I wouldn't write any of that. That's just to put in your head what the graph's going to look like before we start. The actual work is just intercepts. So you've been doing intercepts now since grade 10. We've done a bajillion of them last year. I'm going to start with the y because it's the easiest. I like it better. How do we calculate a y-intercept? And again, I wouldn't normally show this work. Because I put -0 and it makes me happy. But we're just not going to talk about it. Again, I would not normally show this calculation. I would jump straight to what's the intercept? 0. And again, just like last unit, I like to write this as a point, just to remind myself it's a point I'm going to graph. It's nothing else, not an asymptote, it's not anything. It's just a point on the graph. They don't. No. Well, you can have holes in polynomials, as we saw in last unit. X-intercept. How do we do an x-intercept? Put y equal to 0, solve for x. Oh, how do we factor a cubic? Yeah, I grown too. We guess and check using remainder theorem or factor theorem. We want to find one that gives us 0. Then we take the one that we know and we use synthetic division to find the rest. And then we take the answer from synthetic division and factor it. It's the only way to solve for the x-intercepts. So this is factoring cubics from yesterday. How many ways are there to solve a quadratic? I've asked you that 100 times already. How many ways to solve it? There's 5. What are the 5 ways to solve a quadratic? Completing the square. Factoring. Quad formula. Square root and graphing. How many ways are there to solve a cubic? 2. Factoring and graphing calculator. And this is not a graphing calculator question. So there is one way to solve a cubic. If this was easier, I would show you. If this was easier, I would show you. Be quiet. If this is easier, I would show you. Pick a number. 1 cubed. -5 times 1 squared. -6 times 1. Don't like it either. What?
But I can already see the
Shh. Pick another one. Oh, who is in charge? You or me, mister? Thank you very much. Okay, -1 cubed. Ooh, I heard 1 and -1. Let's find it out. So -1 cubed would be? And then you'd have a negative in front of the -1, which would give you 1. -1 squared times -5. -1 times -6. Don't worry, I feel the same. -2, okay. -2 cubed times the negative. -2 squared times the -5. -6 times -2. Again, I like to write the factor here so it's visual because you're going to tend to forget about him, and he's really, really important with what we're about to do. We can't forget about him. What's the actual factor? Okay, got 1. How do I get the rest of them? What would you like to put on the outside? What would you like to put on the inside? What are the 2 things we need to double check? Order, missing terms. So I don't have a constant. Does that matter? No, I could put a 0 there if I wanted to. It's just not going to matter in this question. Okay, drop the -1. -2 times -1. -5 plus 2. -2 times -3. -6 plus 6. Built-in check, 0.
But that's not the final term. The final term would be the 0 at the end.
So if I put 0, 0, 0, it's going to give me the same thing, right?
Well, it wouldn't be 0, 0, 0 because it'd be 0 times -2, which everyone knows
Is 0. Oh, he set me up there. He totally set me up there. How do I get the answer out of this? So what does this do for me? Woo. What do I got to do with that guy? Okay, there's only 2 terms. Don't want to complete the square because it's not equal to anything, and the only time we complete the square is to solve something. So not where we want to go with that.
common factor factoring.
Yeah, this is common factoring, right? Which is the one you guys never see. So if there's only 2 terms, it's common factoring. What's common between them?
Negative x plus 3.
Agreed? So that means our entire polynomial is f of x equals x plus 2. Negative x I'm going to put in brackets just so it doesn't look like a subtraction, and x plus 3. That's where we stopped yesterday, but we need to go one step further because we're trying to find the x-intercepts. So this now becomes a split and solve question. So I'm going to split the three pieces apart. The first one, x equals negative 2. X equals 0.
Yep. Negative x equals 0, so x is negative 0.
X equals. And again, I'm just going to write those as coordinate points just to remind ourselves they're points in the graph that we're going to plot in a second.
Although we already know that there's a point at the origin.
We did.
Finding the y-intercept.
Now, Simon, do you want to say what you want to say to me way up here that I shushed you on?
Yeah.
Okay, say it.
Could have factored from the beginning.
Yeah, we could have common factored it here, but I knew you guys wouldn't see that. But if you see that there's a common factor, we could have started with that. XXX, right?
Negative x. All that.
Are we good so far? Okay, we got to start drawing our graph. If you got a sticky, grab a sticky. If you don't, draw yourself some axes. That's not a sticky. They stole the stickies? They're monsters. Do you want yellow or do you want blue? If you're not using a sticky and you're using your own axes, you need to draw in 1, 2, 3, 4. We assume with this that their units of 1, so we're not going to. So all we have is some intercepts here. So let's plot. We've got 0, 0 for the y-intercept. Right, we've got negative 2, 0. And we've got negative 3, 0. That's all we have. That are the x and y intercepts. So the reason we did steps 1, 2, and 3 is you're picturing in your head what this got to look like. I know the left-hand side points up, and I'm just doing it in pencil light for now. How do I know the left-hand side points up? Because it's negative, because it is an odd polynomial and the leading coefficient is negative. I know the right-hand side has to point down somewhere. What do I know in between? Well, I know where there's a min and when there's a max because I drew the little graph before. What has to happen between these 2 points? It has to be a min in order to come back up. What has to happen between these 2 points? It has to be a max. The problem is I just don't know their height. I know they're there somewhere, and I know the left points up and the right points down. I just don't know how high they are. That's all I need to do for step 5 is figure out how high they are. Well, I know that, for example, the min is halfway between those 2 x-intercepts. How do I know that? Because polynomials are symmetric. Remember with parabolas, we talked about how the left-hand side looks exactly the same. So I know the x-coordinate of the min. What does it have to be? Just repeating, where did negative 2.5 come from? Between. So really what we did was took the average of the 2 x-intercepts. I know the max has to be between the other 2 x-intercepts. So where's the x-coordinate of the max? Negative 1, I think you meant. So halfway between the origin and negative 2. I just need to find their y-coordinates. And if I could find their y-coordinates, we'd be able to finish the graph. How do we find any y-coordinate if we have the x-coordinate? Plug it in. So I'm just going to go back to the original question. I'll start with the negative 2.5. This would be a calculator question. We wouldn't expect you to cube negative 2.5. Bless you, bless you. So throw all that onto your calculator. Put all of that onto your oh. No stickies, no calculator, no nothing. Are you sure Bad Ben didn't set you up? Are you sure there's not a kid at Kelvin that's got your stuff right now? Just saying. Just saying. Like, don't everyone calculate at the same time. Like, please, take your time. I heard negative 6.25. 0.625. Can I just round to 0.6? Negative 0.6. Can we get someone to confirm that? We're going to do the same thing with the max, which is at y or x equals negative 1. If I could make a cricket noise, I would.
We're just tired. It's Friday.
But we already did the work over here when we put in negative 1 to test it. Okay, so let's add those points. So negative 2.5, negative 0.6. So it's a little tiny min, and that's okay. And then minus 1 plus 2. And so it's got to come from the top, loop through the tiny min, come through the max, and go down. Right from up here. Oh, because it's got to be in between negative 2 and negative 3, halfway between the two intercepts. Exactly halfway. The book says table of values. I don't call it that. I call it a test point because it's what we called it in the last unit. So if that makes more sense to you, you can write that in. So I would say use a test point between each intercept. Bless you. Bless you again. Again, steps 1, 2, 3 are just to put the graph in your head. We don't write anything down. So first is name it. Cubic. End behavior. I hear down, up, down, up, down, up. So it is an odd polynomial. The leading coefficient is positive. So because I'm visual, I always just put that off to the side because it just reminds me later. If you're not visual, you might not need it there. Picture what it's going to look like. It's a cubic, so we know it's going to look something like this. Again, we don't know the height of those max mins, but we know roughly it's got to have that shape. You don't have to write that down, but I'm visual, so I like to see it. It's completely up to you, but it's not required to get the marks. Step number 1, the y-intercept. So again, just like last unit, I just ignore everything with an x. What's left has to be the y-intercept, so it has to be negative 2. The x-intercepts. So remember that little trick I showed you yesterday that said look at the last number before you start to pick? It has to be either 2 or 1. Why can we not pick a number of 3, for example? Because we need a factor 1 or 2. Pick a number. 1 cubed. 1 cubed. 2 times 1 squared. -1, -2. Happy face. What does that tell us?
It's 0. There's no
And what would the factor be? -1. Good job, paying attention. Synthetic division. One of those two. Confirm. What do we do with that guy? And then don't forget about this guy up here. What's going to happen if you forget about him, you're going to lose an x-intercept. So then this graph is not going to make sense. So just slap all the three pieces together. And we know it's equal to 0 because it's a y or x-intercept. And then split and solve to get the x values. So here's a point, and we got 3 points down here, 4 points to start off our graph. Am I going too fast? No? Okay, so I always start with the y-intercept, so 0, -2. X-intercept, -2, -1, and 1. Do.
Oh, we already know where the min is.
What I do then, because I'm visual, is I, with my pencil, use this just to fill in pencil. I know it's going to come from the bottom. It's going to loop up, down, and go towards the top. If you're not visual, you may not need that, but I just like to have it there, and then now I calculate the actual max mins.
We don't really need to calculate the min because we already know where it is.
Okay, explain that. So why do I know for sure that the y-intercept is the min? Because it's halfway between these two x-intercepts. So I can complete the right-hand side of the graph. I know that's got to be the bottom point because it's dead in the middle of the two intercepts. What about the max? Do I need to calculate it? Okay, I know it's x-coordinate. Where does it have to be? Has to be in between those two, so the x value has to be -1.5. What do I do with that -1.5? Back into the original. Oh, seriously? Somebody already calculated it? Who said that? Who said it? Oh, I'd love to hear. Say it again because I missed it. Point. Oh, same as the other one, coincidentally. Can we just confirm the 0.625? Like, really, you checked it, or you just said, yeah, okay, very good. So then I know it's got to be just a little tiny little guy there. And so there's the other half of my graph. Didn't ask for it. Plus, polynomials are always XER, both of them, because there's no asymptotes, there's no holes, there's nothing going on. How are we doing so far, besides that these take time and paper? Okay, let's look at number 4. usually when people see an example like this, they freak out. What is this? We have not done one of these. We have not learned one of these. This makes me happy. This is already factored. They have done all that work for us. They've decided to jump right in at the end of the synthetic division. Done. Like when you see this, seriously, there should be a dance of joy because they have done all the work for us.
How do we get to y-intercept?
I'll just hang on, breathe. It does make it a little bit harder to figure out the degree and what the shape's going to look like because you have to do a little bit of math in your head. So we know if we had an x times an x times an x, that would give us x cubed. Again, I normally wouldn't write this, but just want to show you for the example what's going on in our head. We know that that's the only maximum amount of x's we're going to multiply together, so we're going to have an x cubed. Because none of them have coefficients, it's going to be a 1x cubed. So is that a positive or a negative leading coefficient? That's a positive, so now you need to think of an odd graph, positive leading coefficient. And then I just picture the graph. We know that it's going to be cubic. So we know it's got that swoop. Okay? All of this is in your head. You can write it down if you want to, but you're not required to. With me so far? Now I'm going to highlight this part because I wrote it specifically like this. The question would never have it written like that. Hello. Normally, how would we write this? That's the way normally it would be written because we would always simplify it. When a binomial has an exponent, it's called a multiplicity. When a binomial has an exponent, it's called a multiplicity. And what that means is it has a repeating x-intercept. Because if we were to solve and factor that, or factor it and then solve it, we would have x plus 3, or x equals 3, x equals 3. That's what it means. It's a repeated x-intercept.
Is that why there is no maximum min on the base graph? Because
No, completely different. It's just because of the values that are in there. Because there's no x squared, no x, no other terms. We can have two different kind of multiplicities. We can have an odd multiplicity or an even multiplicity. So example below, if I've got an exponent that's squared, that's an even multiplicity. I could have a repeating one 3 times, which is an odd multiplicity. Still with me so far? If you have an odd multiplicity, the graph will cross through the x-axis. If you have an even multiplicity, the graph will not cross through the x-axis. Let me show you what I mean. Both of these have a repeated root at x equal to 1. So we know something is going on at 1. Because this is an even multiplicity, what it says is it's going to come from the top, it's going to just touch the x-axis and bounce back up. That's why a parabola looks the way it does. If we have an odd multiplicity, it comes from the top as well, but it actually crosses through the point and goes back down. That's the difference with the multiplicities. If it's odd, it comes to that point and bounces back up. It just sits on the point. If it's an odd multiplicity, it actually crosses through. Are you with me so far? Same steps as before, even though it's already factored everything else. We've done steps 1, 2, or 3 here. We go to y-intercept. Y-intercept is just the same as before, that we take every x and we make it equal to 0. So I'm going to keep these brackets and put 0 plus 1. And the second bracket is 0 minus 3. And then you can either use the squared or you can use the other bracket. It doesn't matter. It's going to be the same thing. And then we just bedmass it. So brackets come first. So 0 plus 1 is 1. 0 minus 3. And after brackets comes exponent. So I'm going to do this negative 3 squared first. So I'm keeping that 1 in front, not touching them yet. What's negative 3 times negative 3? And then the multiplication, what's 1 times 9? 9. So I have a y-exponent or y-intercept at 0, 9. This is the part that's the most exciting because it's already factored. They've done that guess and check. They've done that synthetic division. They've done that factoring. All we need to do is split and solve it. And I'm going to split and solve with the simplified form just to show you how that works. So I'm going to take x plus 1 and x minus 3 squared, split them into two sides. Left-hand one, x equals minus 1. So nothing, no big deal there, nothing unusual. It's this one that tends to freak people out. How do we get rid of a squared? What's the opposite of squaring something? Square rooting it. So on the left, I'm just left with the x minus 3. On the right, what's the square root of 0? No big deal, the squared's done now. What does x have to equal? Grabbing your red pen. Does the graph cross through 3, or does it sit on 3 and bounce back up? This is sitting. Do you understand what I mean by sitting? Why? Because the multiplicity was 2. Let's just imagine this had been a 3. Then we would have come down here, we would have gotten rid of a cubed by cube rooting each side. It wouldn't have changed the answer, but instead of sitting on 3, it would have crossed through 3. That's the difference with the multiplicities. Grab your sticky. I've got 0, 9. And I've got negative 1, 0, and 3, 0. I know from what we brainstormed up here, which maybe you didn't write down, maybe it's just in your head, which is fine. I know it comes from the bottom. It's got to come up through this point. What happens when it comes down to the last x-intercept? It just bounces. It just bounces right back up. What I don't know is how high it goes here. That's what I'm not sure. How do I know this is not its highest point? Because it's not in the middle between the two. So I need to go in the middle between negative 1 and positive 3. What's the middle? Is 2. No, it's 1. Are we good so far? What do I need to find? I got the x value. What do I not know? We need to plug it in. So I'm going to go back to our simplified form, and I'm going to plug in 1. I went to 9. Crap. So we come from the bottom, loop through, bounce back up. There's your cubic. I missed the point. Shh. Do you understand this idea of multiplicity? If it is even, it bounces. If it is odd, it sits. Sit and bounces is the same thing. If it's odd, it crosses.
How can the maximum be lower than the actual y?
Because sometimes cubics aren't symmetric, so sometimes it's a little higher, but in your world, we're just going to ignore that. Sometimes it's not quite in the middle. Don't give me that face. I did not make this up. Sometimes it's not quite. We just ignore it. It's not. It's not. Just go with it.
Can you drive the actual drawing?
That is the actual drawing. Well, that's better? That makes you happier? Sometimes cubics aren't symmetric. I'm actually kind of feeling like this would be a good place to stop and then finish it Monday in the morning. I feel like rather than rush through and blah. I feel like it's a good place to stop, but really it's up to you guys. I can keep going if you want to. I could keep going at 5 o'clock tonight. I could keep going forever. Okay.